video notes 10-2, and we're going to do some calculations. So your book connections are in chapter 16, and Multato suggests doing the self-check. All right. So water is in equilibrium with itself. What? Water is actually a mixture of water, H plus, and OH minus. So we can write an equation for it. We have H2O, liquid turns into H plus ions, aqueous, and OH minus ions, aqueous. All right, I said equilibrium, so I need that arrow. Okay, we can write that differently as H2O liquid runs into another H2O liquid particle. And in equilibrium, it makes H3O plus ions and hydroxide ions. So, what's the same? This and this mean the same exact thing. So we can write a K for this. The K for this is H plus times OH minus divided by, liquid, nothing, okay? Or we can write it as K equals H3O plus times hydroxide ions and just liquid over there. So either one, it's the same thing. So because this is a K for a very special substance called water, we call it a KW. KW. Now, the cool thing about it is that no matter which one you do, because they're both the same, you always get 1 times 10 to the negative 14. Right? So the constant for water is 1 times 10 to the negative 14. And if it's just water, you have equal amounts of this and this. Good. So we have the pH seesaw. If we have just water, then the seesaw would even out at 8. And we'd have 8, sorry, I said 8, I meant 7. We'd have a pH of 7 because the H plus and the OH minus would be equal. But if you put an acid into water, you get more H plus than OH minus. So as one goes up, the other goes down. So as the hydrogen concentration goes up, the pH becomes 1, 2, 3, etc. As the hydroxide concentration goes down, the pH becomes numbers 1 through 6. But what if the hydroxide concentration goes up? Well, look what happens to the pH. It gets to be big numbers because the hydrogen concentration is going down. It's all balance in water. Woo. So here are some equations that you'll have to be able to use. You can write them all down now. You should have this one already in your notes and this one. We're going to use them today. This is new, pH plus pOH equals 14. This one we just saw, this is the KW. Right? And then these are new. So what's the diff? It's just that you can talk about solutions in terms of hydroxide instead of hydrogen. Look at this. This is the diamond, the beautiful diamond of acids and bases. Okay? And so you can see how these equations connect. If you have POH, you could turn it into OH minus. If you have OH minus, you can turn it into POH. So you could follow the arrows and find the formula you need. Okay, where does H plus and OH minus come from? Well, if you have a strong acid, then all of the H plus comes from all of the acid because it 100% ionizes. So here's what I mean. HA goes all the way to H plus and A minus, 100%. So if you put in 5 molar of this, well, and it all ionizes, it's going to all go away and you'll get 5 molar of H plus. So we can calculate the pH of a strong acid quite easily by seeing the concentration of the acid equals the concentration of H plus because all of this acid breaks up into H plus. So we just take the negative log of 0.00356 and we find out that the pH of this acid, because it's strong, is 2.45. Right? What about base? Same thing, except it's hydroxide instead of hydrogen. So if we want to know, we know that the total concentration of a base is the total concentration of hydroxide, because what do bases do? Bases that are strong, okay, come from group 1 and 2 hydroxides, make A plus and OH minus. But if we had 0.51 molar of this, it would all ionize because that's what strong bases do, and we get 0.51 molar of hydroxide concentration. So if we want to know the pH of this solution, we could say, well, POH, careful, look, it's POH because it's the negative log of the hydroxide, 3.45 times 10 to the negative third, gives us 3.61. Be careful, that was POH. But now that we know that pH plus POH equals 14, we can find out the pH by saying 14 minus 2.61 gives us 11.29. And that's a base. I'll tell you, a base. Okay. So we can convert any of these concentrations into pHs or POHs or concentrations. So let's do it. It's 0.15 molar H2SO4. So this is an acid and it's strong. How do I know? Because I memorized 6 strong acids and this is one of them. So I know that H plus is 0.15 molar because all of this turns into that. Okay. So the pH is the negative log of 0.15 and the pH of this solution is then 0.82. Right? All right. Here's another example. If the pH is 12.77, then it's telling you directly that all of the pH comes from H plus. So we have to take 10 to the negative pH exponent. So we say 10 to the negative 12.77. In your calculator, don't forget to caret it. And you get 1.70 times 10 to the negative 3. Wait a second. Oh, yeah, it does. Molar. Now you might be saying to yourself, that's a small number, but it is because the pH is 12.77. So when the pH is 12.77, let's go back to the seesaw. The pH is 12.77 is because there's a lot of hydroxide ion. Funny how that works out. I know you're laughing. All right, find the POH. So here, it's 1.51 times 10 negative third molar NaOH. We want to know hydroxide. Wait, we know hydroxide. Hydroxide is 1.51 times 10 to the negative third molar. So then POH is negative log of 1.51 times 10 to the negative third molar. Okay? So that means the POH is down 2.82. And then to find pH, we would say 14 minus 2.82, and we get 11.82. So this is a base. All right. Now, if you know the hydroxide, you can get the POH. So do that one. You do. You do. Okay. All right. Here we go with OH and pH. So pH is 3.22. I want hydroxide. Well, I know that pH is directly related to hydrogen ions, so I can do 10 to the, I'll put the caret in, so you put it in your calculator, it's 8.32. So the hydrogen concentration is going to be 10 to the negative 3. We'll put it in 10 caret negative 3.22, and I get 6.03 times 10 to the negative 4th molar. All right. But I want OH minus. So I would say that OH minus, and this is the relationship over here. I have H plus. I want OH minus, so I gotta say 1 times 10 to the negative 15 divided by 6.03 times 10 to the negative 4th. And I get 6.03. And hydroxide is 1.66 times 10 to the negative 11 molar. Okay. I want you to try this one. There's a couple ways to solve it, but you try. You try. Right? Here's your triangle. I said triangle is a diamond. All right. So we did one of these already, but I need to find hydroxide given hydrogen ion. Okay. The hydroxide is going to be 1 times 10 to the negative 14th kW for water divided by 6.33 times 10 to the negative 4 molar. Right? Plug that in the calculator. You get 1.58 times 10 to the negative 11 molar hydroxide. Alright, so pH has no units, pOH has no units, but all concentrations have a unit of molarity. Look, it's one for you to do. You can do it. Remember, this time you're looking for H. Alright, so those were calculations with strong acids and strong bases, because you know the concentration of the acid or base tells you the concentration of hydrogen or hydroxide. But what if you have a weak acid or base? Well, then you get equilibrium. Okay, so what is the pH of 0.42 molar acetic acid solution? So we need to write the dissolving equation. I said dissolving, but what I really meant was the acid dissociation equation. You know, this is in water, and that it ionizes or dissociates to be H plus and C2H3O2 negative. Yay, acetates. Okay, so then we can write a Ka. This should be up here. So Ka is products, H plus times C2H3O2. So what is a Ka? It's an equilibrium constant for acids. So you do products over reactants, HC2H3O2. Okay. So what do we do now? Well, we have to figure out the Ka because it's not given in the problem. There's a table for that. So I'm looking for acetic acid. Here it is. Oh, it's the Chiku version of it. Right? It says that the Ka is 1.8 times 10 to the negative 5. So let's go back. We know this equals 1.8 times 10 to the negative 5. All right, what should we do? This is Harbin. Let's ice it. Right. So we'll ice it by having our acid, HC2H3O2, our hydrogen ion concentration, and our acetate ion. Ooh, right? So this is going to be initially 0.42 molar. And we've got none of that. But that's got to change, I tell you. Minus x plus x. So at equilibrium, we're going to have 0.42 minus x. Then we're going to have x of that next to that. So let's plug it in. X times x divided by 0.42 minus x. All right, we'll do some magic math here. I'm going to bring this to this side, distribute the 1.85 times 10 to the negative fifth into the parentheses, and I'm going to get x squared plus 1.8 times 10 to the negative fifth minus x minus 7.56 times 10 to the negative 6. Okay, you might be saying to yourself, that equals 0. So I solved this to get this. So there's a couple ways to solve this, but the one way you can use is your equation program on your calculator, or you could use the quadratic formula. And when you do that, you find out that x gives you 2.74 times 10 to the negative third. All right, and x is molarity, and it is the hydrogen ion concentration. All right, so we are ready to go. pH equals the absolute log of hydrogen ion concentration. So it equals negative log of 2.74 times 10 to the negative third. pH of this solution, I know, 2.56. Okay, so that acetic acid solution's pH is 2.56. We had to do that because it was weak. All right, so I talked about this Ka table. We used the number off it already. You'll get one for class. But if you notice, this Ka is very large because, look, it's one of our strong acids. And so that means that everything turns into products. And when you do products over reactants, you're going to get a huge gigantic number. and a very small number here, so we can't even really measure these Ka's that easily. Right? But then, when you get to here, what you're finding out is that there are more reactants than products, right, for Ka's that are small. So small Ka means that it doesn't dissociate much, so there's more reactants than there are products. What about Kb? Same thing, different thing. So here's a base, and the Kb for this base is 1.8 times 10 to the negative fifth. That means when this goes into water, we have NH3 and H2O, right? You're going to make NH4 with plus charge and OH minus, right? And this is a liquid, and this is aqueous, and this is aqueous, and this is aqueous. So when you do products over reactants, it's 1.8 times 10 to the negative fifth. That means there's more reactants. Okay? So, with bases, if you want to calculate the pH of a weak base, you need an equation with water in it. So we would take N2H4 aqueous plus some H2O, because the H2O is going to give the proton, because a base is a proton, is a hydrogen taker. So N2H5, yep, we get another one, and plus charge, it's going to be aqueous, plus OH minus, and that's also going to be aqueous. So I'm going to write the Kb here. I don't know why I put it there. It's so far away. So we have products, N2H5 plus times OH minus divided by, oops, we don't need H2O because it's a pure liquid, the concentration of N2H4. You might be saying to yourself, what is the Kb? Well, let's look it up. Hey, it's hydrazine, and its Kb is 1.7 times 10 to the negative 6. 1.7 times 10 to the negative 6. So we can ice this up. We've got N2H4. We've got N2H5 positive. And we've got OH minus. Right, we started with 0.35 molar of this. None of that, none of that. That's all. Well, it's going to change because some of that's going to dissociate. And we'll get that in there. And then we get to equilibrium. 0.35 minus X, and X. So let's put it in. X for that, X for that. And 0.35 minus X for that. So what we do is what we just did before, put it so that we have a quadratic, and then we find out that we're going to get, I'm going to write up here so you can see a little better, x squared plus 1.7 times 10 to the negative 6x minus 5.95 times 10 to the negative 7 equals 0. So now we got a A, we've got a B, and we've got a C for the quadratic form. You can use that equation solver on your calculator, but what you find out is that x equals 7.693 times 10 to the negative molar. Now here's where you got to be careful. X represents what? Well, it represents hydroxide and this ion. What are we interested in is hydroxide. So this is the hydroxide concentration. What do we want? We want pH. So you could do this a couple ways. I say we take negative log of the 7.693 times 10 to the negative 4, and we get 3.11. What is that? That is POH. Right? And so then 14 minus 3.11 equals the pH, which is 10.89. pH. Right. There's a lot going on here. So we got to write an equation. Write an equation. Write a KB. Write an ice table. Solve for x. You're going to use quadratic to do that. And then take that x and know what it means. If this is a base, X is hydroxide. Back here, X was hydrogen ion. Right? Once you know that, then you have to calculate what's X for. This was pH. So, oh look, it's the acid-base diamond. You can draw it, you can write it, you can use it. Or you can memorize the other formulas and know how to use them. So, to review, calculators rock, know your math equations, indicators are colorful and use the Chatelier's principle. pH is actually used in real life to diagnose problems. Okay. All right, so all this stuff we're doing with pH, well, it's going on. Hopefully you don't have blood poisoning, but there's a pH in your blood system. pH for soil. pH has to do with antacids, swimming pools. Holy moly, lots of acid-base chemistry going on in your life. So make sure you do what Miltato asks you to do and self-check, self-check, self-check. So do the video, do the self-check if you get it. Oh, look, it's the objectives, the targets, the what you're supposed to learn. So hopefully you learn them. Peace out.